Hello, everyone. How are we doing today? Doing all right? Okay, so the material for today is a continuation in Chapter 3. It's going to be the last bit of quote-unquote new material that we'll be discussing, at least in terms of techniques to solve differential equations. There are a couple of other sections that we'll talk about next week that are going to be applications of what we have learned for this class of differential equations. So we'll be talking about vocabulary, some physics, and other situations that arise as a result of being modeled using the class of differential equations that we've been learning how to solve up to this point. Um, and then talking about some special cases that arise based on certain configurations of systems and things like that. But in order to set that up, we need to handle this last case here. Okay, so we're going to be looking at non-homogeneous differential equations of this form. Okay, and the technique that we're going to be using will work with any type of G of t. Last section, we talked about finding particular solutions if G of t had some nice properties to it. Here, we don't need G of t to have any particular niceness involved in order for this technique to be applicable. All right. So what we're going to do is we are going to start off with an example and then show the theoretical requirements for our solution to have the form that we want. Okay. So we'll start with the differential equation y double prime plus 4y, and we'll say that it equals 8 times the tangent of 2t. Okay? Now, this right-hand side here has bad properties compared to what we were talking about last lecture, because if I start taking derivatives of this thing, I'm going to get nasty stuff. The derivative tangent is secant squared. Okay? Then I have to take the derivative of secant squared, which is what it is, right? So we're not going to get something that I can make a reasonable guess for. So we're going to end up using a different technique. And the way that we're going to set this up is by doing the thing that we normally do, which is solve the homogeneous equation. Our roots for the characteristic equation are plus or minus 2i, which tells us that the homogeneous solution is going to be C1 times cosine 2t plus C2 times sine 2t. Okay. So the short version of the story for dealing with our right-hand side here is that we are going to employ the reduction of order technique that we did, D'Alembert's method, from a previous section. Okay, except we're going to do it to both members of our fundamental family of solutions simultaneously. Okay, effectively what that means is that we are going to make the guess that our solution has this form. Okay, there are unknown functions, u1 and u2, such that this is a solution to the differential equation. And I want to find what has to be true about u1 or u2, or find the functions u1 and u2 that make this work. Seems sensible? Okay, so what we're going to need to do is put this together and establish a condition under which we can figure out how to set this up. First thing that we're going to do is differentiate this expression. Okay. Derivative of the first function, leave the second alone, plus leave the first function alone, takes the derivative of the second, and then likewise for the second part, we also do the product rule. Okay, so we write all this out. All right. We can rearrange this expression so that it looks like this. All right. Oh, hold on. Let me be a little bit more careful about the setup here. So the thing that we know is that if I take this and plug it into my differential equation, what I'm going to have to get is g of t. Okay. So one of the conditions that I have is that this equation is going to have to give me g of t when I plug it into the differential equation. All right. The other thing that I'm going to need, because I need to have a system of two equations and two unknowns, because these are unknown functions, I'm going to have to figure out some reasonable secondary condition to impose on the problem in order to help me find a u1 and u2 that works. So that's what we're looking for right now, is a way to say, if this is true, then this will give me what I want. Okay? Now, what we're going to do is we're going to take this expression here. Sorry. I'm going to rearrange this. As u1 prime t times y1 plus u2 prime t y2, and then have the rest. Okay. What I'm going to do is I'm going to impose the condition that this is equal to 0. Okay. If we do this, then when I go to take the second derivative, I'm going to have a much simpler expression to compute. Okay. So that reduces my expression for y prime And then after that reduction, we can look at what the second derivative is going to look like. Okay. Leave the derivative of the first function, leave the second function alone. Plus the first function left alone times the derivative of the second. Likewise over here. Make sense? All right. Now, what we can do, okay, is we can take our expressions for y and y double prime, and then figure out that, make sure that we have the right sort of thing for our differential equation. Okay. So we want y double prime plus 4y and in order for this to work out exactly the way that we want it to in this particular case, we're going to need to substitute in what actual y1 and y2 are. Okay. So for y double prime, we're going to have we're going to move these terms in the front. Okay. So u1 of t, and then this is going to be y1 is cosine, so this is going to be -4 cosine 2t. They take its derivative twice. Then u2t times -4 sine 2t. They take sine's derivative twice. And then plus u1 prime t. The derivative of cosine is negative sine. And then the derivative of sine 2t is 2 cosine. Make sense? Okay, second line here. I'm taking 4 times y. Okay, that's 4 times u1 cosine 2t plus 4 u2 sine 2t. Those terms are going to add out. And so what I'm left with over here is -2 u1 prime t sine 2t plus 2 u2 prime t cosine 2t. And this is going to be equal to my right-hand side for my equation above. Make sense? Okay, now, simplified, all this says is that we have u1 prime t y1 prime t plus u2 prime t y2 prime t is equal to g of t. That's, these parts are over here, right? And I know I wrote in the sines and cosines because we needed to show explicitly that this stuff added out. But we get this expression here, okay? Now, what this gives us is two conditions that we can set for our function, okay? We see that u1 prime and u2 prime show up in both of these, and we know what y1 and y2 are as well as their derivatives, okay? So this is a system of two equations and two unknowns, all right? And I had to plug in some specific information for this particular problem in order to kind of demonstrate what happens. I could have left everything completely symbolic and shown that this part always adds out. But the basic idea is that we're always going to get something that looks like the two orange circled equations. Okay? And that's going to be the basis that we use in order to set up variation of parameters. Okay? We're going to start here. All right? So I have u1 prime t y1 of t plus u2 prime of t y2 of t equals 0. The second equation is y1 prime of t, or sorry, u1 prime of t y1 prime of t plus u2 prime of t y2 prime of t, and this is going to be equal to g of t, which is the right-hand side for our non-homogeneous equation. Okay. This can be rewritten as a matrix equation. Where I go across the row and down the column, multiplying term by term and adding up, gives me exactly the first equation. u1 prime times y1 plus u2 prime times y2 equals 0. Same thing on the bottom. Across the row, down the column. u1 prime times y1 prime plus u2 prime times y2 prime equals g of t. Okay. So when you start these problems, you solve the homogeneous equation, and then you write this down. Okay. And then our method will proceed from the matrix equation. Okay. The book does not present it this way. It just gives you a formula for the next part that we're about to write down and expects you to memorize the formula. I think the formula is much more difficult to memorize than setting up the matrix equation and then using the technique that we're about to use. All right. Another thing that I will say now, so I don't forget to mention it, because I might accidentally do it for the next example without saying something. It's not uncommon to use U and V instead of U1 and U2. If you use U and V, your handwriting better be good enough for me to be able to tell the difference between your U's and V's. Okay? Because this isn't going to cut it. All right? So I write mine cursive looking so that they can be distinguished. You don't have to do that if you don't want to, but you have to be able to, I have to be able to tell the difference. Okay? So if handwriting is a problem, and if you write, even if you just write too fast, you know, it can be a bit of an issue. So, all right. So for this problem, we have cosine of 2t and sine of 2t and negative 2 sine of 2t, 2 cosine 2t times u1 prime, u2 prime equals 0, and then 8 times the tangent of 2t. That's where we started, right? Okay, so we have a matrix equation. How are we going to solve it? Kramer's rule, because that's what I told you to practice, right? So for Kramer's rule, if we want to find u1 prime, what we're going to do is we are going to set up a determinant where we keep the second column, but we replace the first column with the right-hand side of our matrix equation. Okay? And then in the denominator, we compute a second determinant, which is cosine 2t, sine 2t in the first row, and then negative 2 sine 2t, 2 cosine 2t in the denominator. I want to point out that this denominator is the Wronskian for y1 and y2. Okay, so if you want to compute the Wronskian separately before getting into this stuff, that's fine. All right, but it's the Wronskian. So we can now keep moving forward here. In the numerator, we are going to have 0 times 2 cosine 2t minus 8 tangent 2t sine 2t. This times this is 0 minus this times this. Okay? In the denominator, we're going to get cosine 2t times 2 cosine 2t minus negative 2 sine 2t times sine 2t. So the denominator is just 2. And our quotient is negative 4 times the tangent of 2t sine of 2t. What did I mess up? Right, but the 2 factors out. Yeah. Okay, we all agree. Yeah, there's a lot going on here. All right. As I mentioned, I talk and write and think and look up, answer questions. All right, I can get off track. So don't have a problem with people double checking me on stuff. Okay, some things to think about before we proceed with this. It might simplify somehow. Okay, maybe it does, maybe it doesn't. All right, maybe tangent times sine is an integral we can handle. Okay, but you need to start thinking about what's the easiest version of this that I'm going to have to work with, because we're going to have to integrate this to figure out what U1 is. All right, that'll be the next step. But before we get there, let's figure out what U2 prime is. Here we replace the right column, and the left column stays cosine 2t, negative 2 sine 2t. And since we've already computed it, our Wronskian's 2. So we're going to get cosine 2t times 8 times tangent. As we just mentioned, tangent has a cosine in the denominator. So this is just 4 times sine of 2t. Make sense? All right. So we have u1 prime of t that's equal to negative 4 times the tangent of 2t sine 2t. This is something that we're going to need to integrate, right? And no holds are barred when it comes to what kinds of calculus 2 integrals we might find here. All right. This is where all of the stuff from chapter 7, at least in the textbook that I taught calculus 2 out of, is in bounds here. Okay. For this, I mentioned that we can think about tangent as sine over cosine. If we do that, we end up with sine squared in the numerator. Okay. It might be helpful to use the Pythagorean identity for sine squared, rewriting it as 1 minus cosine squared. That gives us 1 minus cosine squared over cosine squared, 2t for everything, of course. Then I can write it as 1 over cosine 2t minus cosine 2t. These are things that I know how to integrate. Right? They're usually not this bad, but Okay, this is more about doing the algebra so you don't have to do the calculus. Okay, and if you don't try to do the algebra first and you just say you resign yourself to integrating tangent times sine, then maybe that's less fun. Okay, but this one, do a little bit of algebra, we end up with something that is eventually stuff where we can just say, I know what the integrals of these functions are. Okay. So theoretically, we know what these antiderivatives are. What's the antiderivative of cosine 2t? Okay. For the antiderivative for cosine 2t is 2 sine 2t, right? Because you use the substitution, you end up with a factor of 1/2 multiplies by the 4, just to be clear. Okay. What is the antiderivative of secant 2t? This is low on the list, but it's one of the ones we should have memorized. It's one of the trig functions, right? Do we not remember? I really hate that form for it. Why do they do it that way? If you ask it what the integral is, you get the formula that no one remembers. All right. But the one that most people remember is that the antiderivative of secant is the logarithm of secant plus tangent. Okay. We again have a u substitution that occurs. And because there's a logarithm here, we need to make sure that we use absolute values. Okay. And then lastly, we need a constant of integration. All right. I know it's not pretty, but here we are. Okay. For u2, we need to take the integral of what was a much simpler expression, right? 4 times sine 2t. We're probably less unhappy about this. All right. Agree on that one? Okay. The way that we find our full solution is to return to the original form. Looks like this. And then plugging in those two expressions that we just found. Okay. Our next step is going to be a simplification step. The thing that we always want to do is write our homogeneous solution back out front. Okay. And if we see, because the C1 and C2, we recover our homogeneous solution, which is a thing that tells us that we're on the right track. Okay. So that'll come first. C1 cosine 2t plus C2 sine 2t. All right. Another thing to look at is that we have 2 times sine 2t times cosine 2t. And then over here, we have a like term. Doesn't always happen, but happens here. And if I combine like terms, what do I get? 0. Okay. So don't lazily do this distribution. Make sure that you're paying attention to simplifications that can occur. Last term we have is -2 times the natural log of the absolute value of secant 2t plus tangent 2t times cosine 2t. Please make sure to write this in a way so that it is not ambiguous what is and is not part of the argument of the logarithm. If it makes more sense to you to put that cosine out front so that you're not confused, that's fine. I'm going to use a dot here to indicate the multiplication. Okay, now, would you have ever have guessed that that's what the solution looks like? Not a chance. All right, that's why we have to do it this way. Okay, if the right-hand side is easier than this, we can make a reasonable guess because we can cover all of the derivatives by constructing a linear combination of the cycle of derivative functions. Okay, here for tangent, we can't do that. All right. So let's continue on with some other examples. All right. By the way, these problems just take a while to do. Okay. So don't get discouraged or bothered by that. I'm going to go ahead and just do that, I think. Okay, so trigonometry is very common for these problems. Yes. No, that's not a guarantee. I'm just picking on these examples because I want to do the kinds of integrals that I know people struggle with. But there's no rule that says that the other problem that I was thinking about doing, but I don't think we're going to have time to do both, was this. Okay, so the y would have been there. That has no restrictions there. Thank you for the question. Didn't mean to get rid of my primes. All right. So the idea here, you write down our characteristic equation. Our homogeneous solution has the form C1 cosine 3t plus C2 sine 3t, because r is equal to plus or minus 3i. All right, and we want to set up our problem here. We have a nasty right-hand side. We're going to go directly to setting up our matrix equation. Okay, so we have this, using U and V this time, and we start working this thing out. So U prime is equal to the determinant of, in the first column, 0 and secant squared 3t, and then in the second column, sine 3t, 3 cosine 3t, divided by the Wronskian of cosine 3t, sine 3t, negative 3 sine 3t, 3 cosine 3t, which is 3. Okay, and then in the numerator, we're going to have negative 9 sine 3t secant squared 3t. And this simplifies to negative 3 times tangent 3t over, sorry, tangent 3t times secant 3t. Because I see sine 3t times 1 over cosine squared 3t. Sine over cosine is tangent. Then I have 1 over cosine. 1 over cosine is secant. Okay. Now we do V. We have cosine 3t, negative 3 sine 3t. In the first column, in the second column, we have a 0 and a 9 secant squared 3t all over 3. Our determinant is going to be 9 times cosine 3t secant squared 3t all over 3, which is going to be equal to 3 times secant 3t. Okay. You have to practice your trig identities. Okay. The reciprocal identities the definition of tangent and cotangent, Pythagorean identities, the or the double angle formulas can be helpful to simplify these expressions. All of those. On an exam, that'd be the kind of thing that if you're dodgy about, you can put on your formula sheet. Okay, but experience and practice, very helpful. Okay. The thing that I can't do for you is practice. So these integrations, using these formulas, doing the simplifications, all of that, that's stuff that has to happen outside a lecture. Okay. Both of these are easy, right? What's U of t? Negative secant, right? But yeah, the derivative of secant is secant times tangent. Okay. And then what about v? We just did this one. Okay. I don't need the absolute values because the domain restriction forces the argument to be positive. We can't forget our constants of integration. Hold on. Wait, what? Oh, yeah. Okay, yes. I made a copy mistake. Thank you. Make sense? All right. So now we plug it all in. U of t, y1 of t, plus v of t, y2 of t. So we have negative secant 3t plus c1 times cosine 3t plus the quantity, the natural log of the secant of 3t plus the tangent of 3t plus c2 times sine 3t. We write our homogeneous solution out front, and then we start simplifying. What's negative secant 3t times cosine 3t? Negative 1. Okay, so we just have a constant as part of our particular solution. And then we have a term that looks like we had from the previous problem. Seems all right. Okay, I want to double check this so that we're not just fumbling around in the dark here. So if we look at what's going on with this expression here. All right. What we're going to do is we're going to say that we have a function f of t and set it equal to we'll use a and b instead of c1 and c2. Cosine of 3t plus b times sine of 3t minus 1 plus the natural log of the secant of 3t plus the tangent of 3t times the sine of 3t. Okay. We'll give a and b values here. All right. Now we're not really interested in the graph necessarily. Okay, but we are interested in is what happens if I evaluate this function. So our differential equation was y double prime plus 9 times f of y, and then we have our right-hand side. Okay. Now, our domain restriction took us between 0 and pi over 6. Okay. Now, I can't actually set it equal to 0 or pi over 6 because that's outside of the domain. But if I move my value here up to numerical computations, you see that all the numbers that I get are extraordinarily small. Okay. Effectively 0. Because most computers can't compute numbers that are smaller than on the order of 10 to the minus 16. Okay, that's a computational limit. And the fact that we're always brushing up against that limit means that for all values of c in our domain, this expression is 0. Okay, which means our solution is correct. Is a way to numerically verify what's going on here. Make sense? All right. How are we feeling? Okay. So let's take a look at this. The characteristic equation for this is r squared minus 2r plus 1 equals 0. This characteristic equation factors. And what it tells us is that our homogeneous solution is equal to this. We agree? Okay. Constructing the matrix equation, we're going to get e to the t and t e to the t. Y1 prime is e to the t. y2 prime is e to the t plus te to the t. That's going to be equal to, or I multiply that by the vector u prime v prime. That's going to be equal to 0 in the first entry, and for the second entry, e to the t over 1 plus t squared. All right. Now we want to set up our equation, or our matrix equation, in order to be able to use Cramer's rule here to determine our value. Since it's not so obvious in this case, let's go ahead and compute the Wronskian before we get into the rest of this. So I'm going to get e to the 2t 1 plus t for that product. Distribute and factor, right? Okay. From that, I will subtract t e to the minus 2, or sorry, from that I will subtract t e to the 2t, which leaves us with just e to the 2t. Now we can write out what u prime is going to be. I replace the first column with 0 and e to the t over 1 plus t squared. I leave the second column alone, so it's t e to the t and e to the t plus t e to the t. This is all over e to the 2t. Zero times this expression, and then minus t e to the 2t in the numerator over 1 plus t squared in the denominator, and then all of that is over e to the 2t. So this simplifies to negative t over 1 plus t squared. That makes sense? Okay. So it may have started looking bad, but it's probably okay. The second part here, replacing the second column this time. First column is just both e to the t, and the whole thing is all over e to the 2t. This one's going to look like e to the 2t over 1 plus t squared, all over with a big division bar, e to the 2t. So we get 1 over 1 plus t squared. All make sense? Okay. So u is equal to the integral of negative t over 1 plus t squared dt. This is a u substitution problem. Agree with that one? Okay. Second one. This is another antiderivative formula that you're supposed to know. It is the arctangent. Or if you prefer, you can write it as tangent inverse. My preference is to write it as arctangent. So, put everything together. There's not going to be any cute simplification this time, I don't think. All right. How are we feeling? Okay. The challenge here is the calculus. Okay. We're testing some stuff you may not have thought about for a while, or it was that one chapter in Calculus 2 that we all just kind of forgot about after we got past it, right? Except for, the other chapter in Calc 2 about series that we also forgot about as soon as we got past it. That's next chapter is series. Okay. So, the recipe here is to practice. Okay. Setting it up as a matrix equation is the thing that I warned you about last time that I do differently than the textbook. Okay. Also at the beginning of the lecture here. All right. You are allowed, if you're doing variation of parameters, just to jump to writing down the matrix equation and then going from there. Okay. The thing that I can't do for you is make you remember, or if you didn't do enough practice back in Calc 2 to be good at doing these trigonometric integrals. The trigonometric integrals happen to be the ones that are more common because they produce some of the more interesting application results. And so we're going to see some of these in particular next week to demonstrate some physical phenomenon that occur that arise for particular types of right-hand sides and their relationship to the homogeneous solutions. Okay, so the trigonometric problems are important because of that aspect of things. All right, initial value problems work the way that you would think they do. Okay, just like we talked about last class, you have to make sure that you include the particular solution as part of determining the initial condition. That can be kind of a pain when you have to differentiate some of these more complicated expressions. All right, you're going to get product rules and stuff. There's no way around it. Okay. Nothing difficult, just things that are tedious. Okay. The difficult part is remembering if you need to put the time in on that, the integration stuff. The other thing that I will mention as part of this is that this technique, even though I didn't preface this at the beginning, heavily depends upon your differential equation being in standard form prior to proceeding. Okay? Variation of parameters doesn't need to have constant coefficients in order to be a viable technique. Okay? If you are given a linear second order differential equation and told what y1 and y2 are, even if they're complicated, if your equation is in standard form, variation of parameters will work to allow you to find the particular solution. Okay? There may or may not be a quiz question about this, where I give you a differential equation that you don't know how to find y1 or y2, but I give them to you. Okay? Put it in standard form, use the matrix equation, find the particular find the particular solution. Pardon me. I've hit my limit of how long I can talk until the weather stays in the 70s for several weeks. All right. So, anybody have any questions for me? All right. We'll leave it off there for today. When we come back next time, we will discuss applications of our second order linear equations with constant coefficients.